let's continue from question 3. Question 3 says you have a channel with a bandwidth of 3,000, with a bandwidth of 3,000 hertz, and the transmit power or the received power at the demodulator is 0.01 of a milliwatt, and then the channel noise has a double-sided power spectral density of 10 to the minus 10, which means that this here is N0 upon 2. It's not N0. If it was single-sided, then this would be N0. But if it's double-sided, it means that this value here is equal to N0 upon 2. So the questions are, first, find the maximum rate at which binary data can be transmitted over this channel using PSK and using FSK. So clearly here we need to know the relationship between the bandwidth and data rate. The case of PSK is fairly straightforward. We know that the bandwidth of PSK is given by 2 divided by the bit duration, or 2 times the data rate. And we know that the bandwidth must be equal to the 3,000 as given in the question. Therefore, it means that the maximum data rate that you can have in this case can only be 1,500 bits per second. So that's fairly straightforward. If the question had said ASK, then the data rate would be the same, because remember the bandwidth of ASK and the bandwidth of PSK are the same. The FSK case is different. We know that the bandwidth of FSK is given by this general expression. It is 2 upon TB plus the separation between the 2 frequencies that are used for transmission. Now, in this case, we have not been given any information that allows us to figure out the 2 transmit frequencies, F1 and F2. Therefore, the best we can simply assume is that the separation between F1 and F2 is such that it is also equal to 2 upon TB, in which case the bandwidth then becomes 4 upon TB. So here what we are making the assumption that if we look at the power spectral density centered around, let's just say F1 is greater than F2, centered around F1, this will be F1, and this will be F2. You have a sine x upon x squared, and that sine x upon x squared would actually do this at F1, and it would do around F2, it would essentially do that at F2. So you have a 1 upon TB here, you've got another 1 upon TB here, you've got another 1 upon TB here, and you've got another 1 upon TB here. So that's why we're using an approximate value of 4 upon TB. However, if we had been given F1 and F2, then what we would use then is the bandwidth would then be this assumes F2 is greater than F1. It will be F2 minus F1 divided plus 2 upon TB. So the assumption in this case is this is F1 and this here is F2, where F2 is greater than F1. Okay, so essentially using for FSK an approximation which says the bandwidth is 4 upon TB, which is equal to 4 times the data rate. It means that the data rate would then be 750 bits per second in the case of FSK. So that's the first part. Then the second part says find the bit error rate. Don't get confused by terms bit error rate, probability of error. They are the same. Right? The bit error rate and the probability of bit error are the same things. So if we need to find the bit error rate for PSK, we know that for PSK, the bit error rate is given by 1/2 error complementary root of EB upon N naught. What do we know? We know N naught. N naught is given. We know the power is given, and we have already now determined the data rate, which means we can essentially work out the energy per bit. It's simply the power times the bit duration. We want the energy expended during a bit duration. It will then be the average power times the bit duration, which in the case of PSK would be the average power, which is 10 to the minus 6. And then the bit duration is 1 upon 1500. So that gives us EB. So now we've got all the variables that we need. So substituting them into our bit error rate expression, we then say that the bit error rate in this case would be 1/2 error complementary, the square root of EB, which is given by this term here, divided by N naught, and N naught is given by this term here. Okay. Notice that N naught upon 2 is 10 to the minus 10. Therefore, N naught will be equal to 2 times 10 to the minus 10. Simplifying this, it means what we need to do is to find the error complementary of 1.826. And we do this by going to the error function tables. If we go to the error function tables, oops, where are they? I think they're at the back. Right, here they are. We want the error complementary of 1.82, 1.8, just check, 1.826, or let's just call it 1.83. So it means essentially we can obtain it by extrapolating between 1.8 and 1.85. And I'm just going to assume that that number is, this is not 0.989, this is not 0.991. So I'm going to just assume it's not 0.99, somewhere between there. It means then that I can then say that error complementary of 1.86 will be 1 minus error function of 1.86, which becomes 1 minus 0.99. I still have this half to contend with. So it means essentially that the error rate in this case will be 5 times 10 to the minus 3, which means on average you're going to have 5 bit errors in 1,000 transmitted bits. So that will be the bit error for PSK. For FSK, we are not given the center frequencies, the transmit frequencies, so we can't really work out the correlation. So we use the error function for the bit error probability for coherent PSK, which is 1/2 of error complementary root of EB upon 2 N naught. And again, we know N naught. So the only thing we need to find is the EB for FSK, and EB is always going to be the power times the time. And then in the case of FSK, our time is 1 upon 750, which means then EB is 10 to the minus 6, the power, multiplied by TB, which is 1 upon 750. So plugging this and the N naught into our expression, we will then essentially have root of EB, which is given by this. This 2 is essentially this 2 here, and then this here is essentially N naught. So this would be equal to our N naught, okay? So we have an EB, we have our 2, and we have N naught. Simplifying this, we will find that it is actually also going to be error complementary function of 1.826, which we've already calculated as 5 times 10 to the minus 3. So the error rate is the same, But don't forget that in this case, FSK is transmitting at a lower data rate, or it's using a higher energy per bit than the case of PSK. Then the last bit is actually find the receiver. Well, the receiver that we actually looked at, which was the detector side for PSK, this was actually the detector which we had. We have one basis function for PSK, which is essentially this cos term. Then we integrate and we sample every bit. But if we have to represent the front-end portion of the receiver, it means the front-end portion of the receiver will be the same as the front-end portion of an AM receiver. So you have your antenna, which receives the signal, and you have initially an RF amplifier, which would be essentially centered at whatever carrier frequency you will have chosen to use, and it will have a bandwidth, which will be the 3000 hertz, which has already been given. So you actually have the bandwidth of the RF amplifier would be 3000 hertz. And then we always heterodyne, meaning we convert to an IF frequency. So you take the signal at this point and you mix it with a local oscillator, where the difference between this frequency and this frequency here is 10 megahertz. And then you will have a signal at this point, which is now centered at 10 megahertz. Which means when you then do your demodulation, you've got to demodulate with a frequency at the IF frequency. So that will be the case of the receiver for PSK. If we look at the receiver for FSK, it will be exactly the same with the front end part. The front end part will be the same. The only difference would be that the demodulation of FSK essentially uses two branches. Because remember, FSK uses essentially two basis functions. In the case where you assume that it's orthogonal, the two frequencies are orthogonal, then your 2 points would be something like that. So you use two branches. The first branch you correlate with cos, the second branch you correlate with cos, but at the two intermediate frequencies, IF1 and IF2. The separation between IF1 and IF2 in this case is 750 hertz, which means in fact, if you have a frequency at 10 megahertz, if you say that that is your carrier, then one frequency is up there and then the other frequency is up there, and the separation between this and the carrier is 375. This is 375, so that the total here is actually 750. So that will be the receiver and transmitter in this case. Okay, any questions on this problem? Okay, if not, then let's. Yes.
Just with regards to the center of frequency that we're using for transmission, when it gets received, do we just thumbsuck a value or?
Well, yes. The problem says make realistic assumptions of the carrier frequency and the IF frequency. So essentially, you can choose what those should be. But of course, there are some something that sort of makes it realistic is that your carrier frequency is going to be much greater than the data rate, as well as your IF frequency is going to be much greater than actually the data rate. And here, what I've just used typical frequencies that are actually used. The 900 megahertz is the frequency band that we use for cellular transmission. We use a number of different bands, but the lowest band is the 800 to 900 megahertz. You could have chosen, say, 500 megahertz or 100 megahertz. That is still fine, because the problem doesn't really actually direct you as to what the frequency should be. And then in terms of the intermediate frequency is significantly lower than the carrier frequency, but greater than the data rate. So you could have actually chosen 20 megahertz as your IF frequency. But bearing in mind that the typical IF frequencies are 70, 21.4, and 10 megahertz. But you could have chosen any. I chose 10 megahertz because it's really the typical IF frequency that is used in a lot of radio systems.
Okay, so then just to confirm, the carrier frequencies and the IF frequencies that we were kind of looking at in the analog case would still then apply in the digital scenario. Like there isn't any reductions for digital.
No, there isn't. Essentially, the front end part of the receiver would really be the same. In a way, the front end part of the receiver is simply determined by the transmission band that, let's say, the regulator, ICASA, is actually determined. So if ICASA is actually determined that for this particular transmission system, your frequency band is 900 megahertz, then that would be, in actual practice, that is what you would use. If it is, let's say, an FM system, your frequencies are around 90 to 100 megahertz. If it is AM, then your frequencies are around the hundreds of kilohertz range. But in this case, it doesn't really specifically direct you in a particular direction. So you can choose any carrier frequency you want and any IF frequency you want.
Okay, thank you.
Okay, right. So let's move on to question 4. Question 4 is actually fairly straightforward. You have a binary FSK system, and you have a bit rate of 1,000 bits per second. But now you are actually given the separation between the two frequencies. So let's say you are using frequency F1 and you are using frequency F2. And in this case, you are told that the separation between the frequencies is 800 hertz. Then determine the probability of error, assuming that EB upon N naught is 5 dBs. Now, in this case, because we are specifically given a separation between the two frequencies, what we would have to then do is, the easiest approach is actually to use the formula which says the bit error rate will be 1/2 error complementary function, the square root of, so all this lot is within the square root bracket of E upon 2N naught into 1 minus R. That is a general expression that applies to any binary modulation scheme. Similarly, remember, we also said that another formula that you could have actually used would be the one that depends on the distance, where we could essentially have used, instead of what is in the square root sign, we could have used actually the square root of d squared, where d is the distance between the two constellation points, divided by 4N naught. And these formulas are given on your data sheet, upon 4N naught. But to use this, you obviously need to be able to actually find the distance between the 2 points, which means you need to actually evaluate it, use some basis function, evaluate the coordinates of the 2 points, and then be able to work out the distance. In this case, it's actually much easier to actually use this particular expression, because the energy E upon N naught is actually given. So this term is actually already been given. And the only term that you need to find is really the correlation. Now, the correlation depends on the distance. And again, this is given in on your data sheet. The correlation between any two sinusoidal signals is actually given by sine of 2 pi delta TB divided by delta TB, where delta is the separation between the two frequencies. So delta is 800. The SNR, which is essentially EB upon N naught, is 5 dBs, which when converted to an actual power ratio is 3.16. And your data rate RB is 10 to the 3, which means that TB is 10 to the minus 3. So substituting this, we'll then have the 2 pi, which will be here, and then the delta is 800, so this here is delta, and then the TB is 1 upon 1,000, because the data rate is 1,000 bits per second. So essentially, this 1 upon 1,000 is actually equal to TB. And we do the same with essentially the denominator, which is the same as this, and we evaluate that. If we evaluate that, we'll find that the normalized correlation rho would be minus 0.19. Substituting that, then we will find that the bit error rate is 1/2. The error complementary function of this here is EB upon N0, which we've actually worked it out, 3.16. And this 2 here is essentially the same as this 2 here. And then we have a 1 minus, and then this here is your correlation, which is minus 0.19. So I have a 1 minus 0.19, which gives me 1.19 times 3.16 divided by 2, and all of them under a square root bracket. So when you evaluate that, we will find that the argument under the error complementary is 1.37. So we essentially evaluate this by using error function tables. So this will be 1/2, which is this 1/2, and then the error complementary is 1 minus the error function. So I need to look up the error function of 1.37 using tables. And then again, I go back to my tables. So now I want 1.37. Now 1.37 is somewhere within here. 1.35 is 0.943, and this is 0.95. So 1.37, I'm going to take it as 0.95. Just make 0.95 in between there. And let's see, is that the one that I used here? Okay, yes, that's the one I used, 0.95. So essentially, I then have the error rate is 1/2 into 1 minus 0.95, and that works out to be about 2.5 times 10 to the minus 2, which means on average, I get 25 errors in every 1,000 transmitted bits. And then the next bit is essentially actually the receiver function. The receiver function would be exactly the same. If it's implemented as a correlating receiver, it would essentially be given by that. And then the front end portion, in this case, I simply put a bandpass filter with a bandwidth of 2.8 kilohertz centered around FC, so that it makes it clear then that I have one frequency there, I have got one frequency there, and then essentially this separation here is 800. Then I need at least on this side, I need 500, because my data rate is 1,000. So this side will be 1 upon TB, and then this side here is also going to be 1 upon TB, which is 500. Remember, the bandwidth is given by, so another 0 here, is given by F2 minus F1 plus 2 upon TB. So this will be 1 upon TB on this side, and 1 upon TB on this side. Okay. Sorry, this is 1,000, not 500, 1,000. Because it's 1 upon TB, which is RB. So this is 1,000, and this is 1,000, which means, in fact, the total bandwidth from there to there will be 1,000 plus 800 plus 1,000, and that is why I have actually a bandwidth of 2.8 kilohertz there. And the basis functions are always going to be given by root of 2 upon Ts, where Ts is the symbol duration, then cos of 2 pi f1t, and then the other one is cos of 2 pi f2t. Okay. Now, bearing in mind actually that in this case it's binary, therefore Tb is actually going to be equal to Ts. So the issue in this case was simply the fact that you would be using this expression to calculate your bit error rate, and in this expression, the only term that you really need is actually R, because EB upon N naught is given. Okay.
Hi.
Mm-hmm.
Sorry, can I just ask, I thought we only used that expression when the carrier frequency was much greater than the data rate. Is that true?
Which expression?
That one that you just circled.
No. This is the expression for the bit error rate of any two binary modulation scheme. It doesn't really depend on the fact that they don't need to be sinusoidal. Essentially, in this expression, your E is the average energy, which is going to be equal to the E1, which is the energy of S1. Whatever S1 is, it will be the energy of S1 plus the energy of S2. Let's call that E2. And then all that lot divided by 2 to average them. So that is what E is. And R is simply given by 1 upon E, where that E is the average energy, and then the integral over a bit duration from 0 to Tb of S1 of T, which is the one waveform that we are using, S1 of T multiplied by S2 of T S2 of T dt. Okay, so whatever S1 and S2 are, you simply calculate E and you calculate the correlation R, and then you plug it into this expression. And that applies to any binary communication system. As long as you know S1 and as long as you know S2, then R is given by that and E is given by the average energy. Now, if S1 and S2 are two sinusoidal signals at two different frequencies, which is what you have in the case of FSK, then R or rho is simply given by this. This is only in the case where you have FSK. But if you don't have FSK and you've got two other waveforms, then what you would essentially do is to calculate your R using that. So let's say, for instance, let's go back to question. Let's say you actually were given this as S1 and this is S2. Well, how would you calculate this? In this case, then, your E is clearly going to be given by the energy of 1 times plus the energy of 2. So the energy of this is 2 squared times 3, which is actually going to be equal to 4 times 3, which is 12. And then the energy of this one is 2 squared times 1, which is essentially plus 4, then divided by 2, which means essentially the average energy in this case would be equal to 8. Then you calculate then your correlation. Your correlation essentially will be 1 upon 8. Then the integral of S1 times S2. In this case, if I take S1 and multiply by S2, then I'll simply have a a pulse with an amplitude of 4, because it will be 2 times 2, but only going from 0 to 1. So essentially, this will be an integral of 4 between the limits of 0 and 1 dt. And if I do this, essentially, I will actually find that it will be 4 times 1 divided by 8, which is equal to 1/2. So rho would actually be equal to 1/2. So I can then use that same expression which says that the bit error rate is 1/2. The error function complementary of root of E upon 2n0 into 1 minus 1/2, which is actually the correlation 1/2. Okay. Now, if I solve for this, I should get exactly the same answer as we actually did in this particular case. In this particular case, this is what I ended up with. I ended up with essentially d squared upon 4 divided by n0. And if I compare it in this case, my E is 8. So this is actually going to be equal to 8. So if I substitute in this case, I'll end up with E, which is, let's just look at the argument of the square root sign. It would essentially be E, which is 8, multiplied by 1 minus 1/2, which is also a half. So this term here gives me a half. So I simply put a 2 here. And then I will have this term here, which is also another 2. And then I will actually have a value of n0. Now, if I simplify this, I simply then get a value of square root of 4 divided by n0. Okay, the 2 and 2, sorry, no, 2 divided by n0. So this 2 and that 2 into the 8 gives me 2. So this reduces to root of 2 upon n0. Compare it then with what I actually have here. I have exactly the same. The 4 into 8 gives me 2, and this here is n0. Okay. So whether I actually use this expression here or I use this expression here, for a binary communication system, I'll end up with exactly the same answer. In a case where the question doesn't require you to determine the basis function and the signal constellation, I actually find that it is actually easier to use this expression, because all you need to find is the average energy, and then you need to find the correlation and then plug it into that expression. Alternatively, you can do the long route by essentially finding your your signal constellation and then finding D and then substituting it into this expression, and you actually find the same answer. Is that making sense?
Yes, that makes sense. Thanks. Can you go to question 3 where we did the FSK bit error rate? Because in that one we used a different formula. I just want to know why, in which case we use either, because this isn't the 2 that you just spoke about.
Okay, right. In this expression, with this case, we use this expression for FSK. We essentially assumed in this expression that the two frequencies are orthogonal to one another, which means essentially the rho is equal to 0. Therefore, you have essentially E into 1 minus rho, which essentially becomes E times 1 divided by 2 n0. Okay. So the only assumption in this case is that the correlation rho is equal to 0. Now, in this particular case, we made that assumption because we have not been given any information that allows us to find the correlation. We do not know the two frequencies that are used, nor do we actually know the separation between the two frequencies. If we knew the separation between the two frequencies, then we could actually have calculated the rho using this expression. And like I mentioned in the lecture, what you find is that in a lot of textbooks, the bit error rate for FSK is actually given as this, right? As root of EB upon 2N0. But what those textbooks do not actually indicate is that they are actually making an assumption that the two frequencies are such that the signals are orthogonal to one another.
Okay, I see. Thanks. And can you just go to the next slide again?
Mm-hmm.
I think the one after that, the question 4. Yeah. How did you do the conversion for 5 dB? Did you use 20 log 10 or did you use 10 log 10?
It is 10. If you have the ratio of two powers to convert them to dB, remember dB is always a ratio of two powers. And the dB is always going to be 10 log to base 10 of 1 power, let's call it P1, or divided by the other power, P2. That is actually what the decibel is. It's actually a ratio of two powers in a logarithmic domain. Okay? Now, if you are not given power, but you are given voltages, then you need to convert your voltages to power, because decibels are always ratio of power. So if you are given two voltages, you would essentially then represent this P here as a V1 squared, and the second P also as a V2 squared. And then V1 upon V2 is essentially the amplitude ratio. So you can essentially then take this 2 here out and then have 20 log to the base 10 of V1 upon V2. It simply becomes 20 log by virtue of the fact that V is related to power using essentially a square. But the actual definition of the dBs is power ratio. And the definition has a 10 log to base 2 of the ratio of the powers that you are comparing. Okay, that making sense?
Yes,
okay.
Thanks.
So in this case, I simply said, I called this here my SNR, and then essentially I then said that this is equal to 5 dBs. I made that equal to 5. Then essentially take the 10 onto the other side, it becomes 0.5. So 0.5 is equal to log to the base 10 of SNR. Therefore, SNR would be 10 to the 0.5. And that is which gives me the 3.16. Okay, right. Let's go on to question 5. Question 5 is actually you are given two constellations that uses essentially some form of 8 QAM, and the distance between adjacent points is 2a. Determine the average transmit power for each constellation, and assuming that the signal points are equiprobable, and then secondly, which constellation is more power efficient. Well, so essentially, to find the power, we essentially find each of these signal constellation points, the power of this signal constellation point, or the energy rather, is actually given. This distance here is root of the energy. It's always going to be root of the energy. the energy of that signal point. This distance here is the root of the energy of that signal point, etc., etc. Remember, in QAM, different points may actually have different energies. Okay. Now, in this case, we are given that the distance between any 2 points is 2a, which means that this here is 2a. And likewise, this here is equal to 2a. And likewise, this here is going to be 2a, etc., etc. Okay. Now, for the second one, we are given that also the distance between adjacent points is 2a. So this here is 2a, this here is 2a, and this here is actually going to be 2a. And this here would also be equal to 2a. So we need to find essentially the average power. So in the first constellation, we can write the coordinates of each of the points and say this here is 0, 2a, this is 2a, 2a, so that the distance between this is 2a. This here is 2a, 0, so that essentially the distance between this is actually going to be 2a. So to find the average energy, we notice that actually we are 4 signal constellation points that will have the same energy and another 4 that will have the same energy. So this and that and this and that have all got the same energy. And that same energy, remember, this here is root of the energy. And this distance here is actually going to be 2a squared plus 2a squared, which is essentially going to be equal to 8a squared. Therefore, this here is going to be root of 8a. The a is not inside the square root bracket. So it means then that the energy of these 4 points are simply given by 4 because there are 4 of them, and then the square of this, because this is root e. And the square of that becomes root 8a all squared. So this gives me the energy of these points. Now, what about the other points? If this and that and that and that have got the same distance from the origin, which means in fact the where this here is 2a and this here is 2a and this is 2a, etc., etc. So essentially the energy of this here is essentially the square of this, so it is 2a all squared for one of them, and there are 4 of them, and then we multiply by 4. So that gives me essentially the total energy. To find the average energy, I have 8 symbols, so I divide by 8, but I need power, then I divide the energy by the symbol duration, so that gives me the power, and in this case, unless my arithmetic is wrong, it comes out as 6a squared upon ts. We do the same for constellation B. In constellation B, remember, this here is 2a, this here is actually 2a, and essentially this here is 2a. It means that this point here has coordinates a0, and then using geometry, we need to work out, first of all, this distance here, because it's related to the energy. But to work out that distance there, we simply notice that this here is a, and this is 2a. So therefore, this would essentially be going to be equal to 2a, sorry, a as well. So this whole thing is 2a, and then this here would essentially then be using the fact that this is 2a and this is a, it means that this has got to be root 3a because this squared plus this squared must be equal to 2a. So this is root 3a. So I know this here is root 3a, and I know this here is actually 2a. It means that this here would be the square of this plus the square of that, which is 4a squared plus 3a squared, which is 7a squared. So it means that that hypotenuse is actually root of 7a. So that means then I can actually calculate my average energy. Again, I have 4 points, 1, 2, 3, 4 that are equidistant, that have got the same distance from the origin. So I will have 4 times 7 root 7a all squared, because root 7a is equal to root of the energy. So the energy would be equal to root 7a then all squared. Then plus, then I notice now that this here and this here are the same, and they actually have a height of root 3a. So I will have essentially root of 3a all squared times 2, because there are 2. Then the last 2 would be this point here and this point here. And for those points, essentially it will be a squared, and this will be a squared. And then there are 2 of them, then times 2. Simplifying all that lot, I end up with 9a squared upon 2 times Ts. So that's the average energy. Now, if I now compare the average power, if I compare the average power of the first constellation and the average power of the second constellation, the average power of the first constellation is 6 times a squared upon 2 Ts, and then for the second one is 4.5 a squared upon Ts. Therefore, essentially, the constellation B will actually have a lower power than the constellation A. Then it's preferable, therefore, to use constellation B. How are we doing? Any questions there?
I have a question.
Right, yes.
Why is it better to have less power in your constellation?
Why is there? Oh, okay. Because essentially it depends. The power depends on where you locate your points in your signal space.
Okay, thank you.
Right. Because essentially the energy that is used when you transmit a particular signal constellation is simply given by the square of the distance from the origin. So if you have a signal constellation point here and you know its coordinates, then this here is actually root E. And the square of this is the energy, which means whenever you transmit this signal constellation point, the amount of energy that you expend is given by the square of this. So quite clearly, depending on how you place your 8 points in your signal space, you're going to have different energy values.
Okay, that makes sense. Thank you.
Okay. Any other question? I just want to go on to the next question. Question 6 is also fairly straightforward in this case. We have a binary FSK system where the S1 is given and S2 is given. So S1 is clearly using a frequency of 21,000 and S2 is using a frequency of 20,000 because this is 2 pi. So this is 21,000 and this is 20,000. And we are actually told that the bandwidth is 1900. And we are given N naught, which is the power spectral density. So the question is, obtain the orthonormal functions and then sketch the power spectral density and then determine the bit error rate. Okay, now very quickly, in this case, if we look at the power or at the frequencies, we are transmitting at a frequency of 21K, 21 kilohertz, and we are also transmitting at a frequency of 20K. And we are told that the bandwidth is 1900. Okay, so this will be 1900. So that's a 9 with the 2 zeros. Now, we are not actually given the data rate. Because we are not given the data rate, we are, however, given the bandwidth. We know that the bandwidth 1900 is actually going to be equal to the separation between the two frequencies, which is this, let's call that actually delta, is going to be given by delta plus a 1 upon TB on this side and a 1 on this side. So essentially plus 2 upon TB, or just simply 2 times RB. Right. We know delta because we know F1 and F2. We know the bandwidth. So essentially we can find what RB is going to be. This is 1900 is equal to 1000 plus 2 RB. Right. So essentially it means automatically we can then say that 2 RB plus the separation between the two frequencies will be equal to 1900. Therefore, RB is going to be 450 bits per second. So we essentially then know our data rate. When it comes to, and then the plot of the power spectral density, you have a sine x upon x centered at 2100, and you've got a sine x upon x centered at 21,000, and the other one is at 20,000. And this here goes to 0 at 450. Did we say 450? At 450 above this, and this will be 450 below this. And likewise with this one, this will be essentially be 450 above this, and this point here will be 450 below that. So that will be the power spectral density. And then to determine the bit error rate, we actually use exactly that same expression, which says the bit error rate will be given by 1/2 error complementary function of the energy per bit divided by, multiplied by 1 minus R, or rho, divided by 2 and divided by N naught. Okay, so the only thing that we need to find here is essentially E and R. Now E is always going to be 1/2 A squared TB, because we are given in this case explicitly a value for A. We are given the amplitude here. So the E would be essentially going to be 1/2 A squared TB, and substituting for TB is 1 upon 450. So this is TB. Then it gives us that as the E. Now the E for S1 and the E for S2 are exactly the same, and they'll be the same as ER. The next one that we need is actually an expression for rho, and we do exactly the same, sine of 2 pi delta TB upon 2 pi delta TB. We know delta. We now know TB, so we can calculate that, and in this case, it comes out as 0.07. So plugging that in, we now have this here is our E, which is 20 upon 45, and this here is essentially going to be my rho, which is 0.07, and this here is given in the question, and it is N0. So that becomes 1/2 error complementary of 1.6, and is then essentially going to be equal to 1/2 into 1 minus error function of 1.6. If I go back to my tables and I look for the error function of 1.6, 1.6 is the error function of 1.6 is 0.976. Okay, is this value here, 0.976. So if I come back here and I substitute uh, 0.976, I think I simply put it as 0.98 if I well, let's use 76. I'm not sure what number I used there. 0.976. Then this term here is 0.024, is it not? So 0.024. Okay, 4 plus 6, 0, 2 plus 3, yeah, right. So that will be 0.024, and then I still have this 1/2 here, and then if I divide this by a 2, I then end up with 1.2 times 10 to the minus 2, which then becomes the bit error rate. Okay, we'll continue tomorrow. I have a call that I need to go to at in a minute's time, so we'll continue tomorrow. Okay, right. Cheers, guys. If there are any questions on this, you can actually ask it tomorrow. Just that I have a call now.
Yes, sir.
Okay, cheers, guys.